Welcome back to A731. In this video, we will continue our discussion of modeling dislocations. In the previous video, I had shown you qualitatively how plastic deformation is mediated by dislocations. Okay? And in the process, we saw that what we call as plastic strain is essentially a measure of the distance between two different elastic energy wells. And these energy wells are separated by these metastable states, metastable energy states, which are indeed what we call as dislocations. And now what we will do in this video is to look at how we would go about modeling these dislocations. Okay, and the way we would model dislocations is as a singularity in an elastic field. To appreciate what that means, what I've shown here in this picture is a cartoon description of a dislocation inside a crystal. So you see that the black dots are atoms which are in a perfect crystalline structure, maybe slightly distorted, that's fine. But these red atoms that you see here, these are outliers in the sense that they do not belong to the crystal structure. So if, for instance, if I look at these four atoms, they all belong to they all form the vertices of a square. Okay, same here, same here, same here, and so on. But if I look at this region, I see that there is a collection of 5 atoms. They do not form the vertices of a square. Okay, so this clearly is a change in the local geometry, and that is a very telltale sign of a dislocation. Okay, so you see that this extra layer that is shown in red is something that is should not be present. It is something that is extraneous to the system, and this is an example of an edge dislocation in a cubic crystal. Now what I'm going to do is I'm going to zoom out of this picture and consider and look at a larger part of the crystal which contains this dislocation also. Okay, if you do that and I scale it back to the same page of the size of this screen, so you see that there are more atoms now, but you can clearly see the dislocation again. Okay, so you have an extra plane of atoms where you're not supposed to have this extra plane. I zoom out even further, the same story. Okay, so all I'm doing now is I'm just zooming out so that I have more and more and more atoms. Now it's a very simple task to imagine the limit when you really come out to a macroscopic scale where you cannot visualize these atoms anymore, but you see a continuum. And in the macroscopic limit, what you will see is that the earlier situation can be idealized as follows. There is a definite plane called the slip plane on which this extra half plane ends. Okay, and in the continuum scale, this extra half plane is a thin line. Okay, so it's just a line which is present, and the dislocation itself is out of the plane of paper. Okay, so for instance, if you remember, if you look at this as a cross section of a cuboidal region, then the dislocation line lies on the slip plane and it is pointing into the plane of the paper, and it is located at this particular point. So the dislocation itself is just this point in this cross section, but in 3 dimensions it's a line passing through that point on the slip plane. This is not the dislocation line. The line passing through this point into the plane of the paper, that is the dislocation. Okay, and what you're seeing here, what is marked as a red line here, is the extra half plane of atoms that you see here, that is introduced into the material. To visualize that better, I've shown here a 3-dimensional version of the same thing. Okay, so you have so I've just taken the previous picture and I've given it a 3-dimensional view. Okay, so you see that there is a crystal in which there is this black square with shaded in grayish blue. That one is the extra half plane, and this red line that you see here which goes through the crystal, okay, that is an example of a dislocation line. Specifically in this example, it is an example in this case it is an example of an edge dislocation. And remember also that to get this dislocation, the way we got it was by actually pushing or shearing the left side of the crystal across the slip plane towards the right. Okay, so if I go back to this picture over here, so you see, if you focus on the top half of the left hand side here, you see that the left part is compressed, but the right half is remaining remains uncompressed. So ahead of the dislocation there is a compression, behind the dislocation there is no compression, and the same thing holds true. So now you see there is no compression here, but these parts are compressed. Okay, so if you were to idealize that, what you would say is that if you look at the slip plane and I take one part of the slip plane, okay, the atoms are above the slip plane on one part, and I shear it uniformly with respect to the bottom half, then the trace, the boundary of that particular region is what I call as a dislocation. Okay, so if I were to word it differently, I take this part, I cut it from the rest of the crystal, I slide it and then paste it back again. Okay, and when you paste it back, there are no residual stresses. And why is that? The picture I want you to have in mind is this kind of a picture. So what you see is that I have indeed taken the top half, I've cut it, slided it, and pasted it back. But there are no residual stresses because what you're getting back is an atom, is a structure where the bulk is in exactly the same crystal structure as before. In the energetic language, the energy hasn't changed really as you move from the initial well to the new well. Okay, except now that we are not cutting all the way through, we are only cutting through part of the crystal. So where does that cut half end? It ends on this particular line, right? So you're cutting until that particular point, and that is where the slip ends. And that trace of that region, the geometric region, is what you call as a dislocation line. Okay. Now what we want to do is we want to model the physics of or the elastic field of these dislocations. Okay. The simplest way to model this is by saying that the gradient in the displacement field can be decomposed into an elastic part and a plastic part. Okay, and again, to understand the rationale behind this, let's go back to our discussion of the the simplified picture of plastic deformation. Okay, so we saw that after removing all the loads, there is still a finite deformation that the body undergoes called the plastic strain. Right now, if I continue loading, what is going to happen is the system is actually evolving in the new energy landscape. So the total strain that you see here at the value of epsilon is the instantaneous strain plus the plastic strain. Okay, and that is what is given here. The total strain is the plastic strain plus the elastic strain, and the stress depends only on the elastic strain. Why is that? Because the previous configuration where you have a non-zero strain is a stress-free configuration. So this strain, the plastic strain, does not contribute to any stress at all. What contributes to any kind of a stress is only the addition to the plastic strain, which is the elastic part, which is what we call the elastic part. So you see that the total strain can be written as the sum of the plastic strain and the elastic strain. And of course, this is the small strains approximation. In a more general case, you would write it in terms of the deformation gradient. Okay, so let's not get into those details for now. Okay, coming back to our model, what we want to do is we want to model the displacement of the body, right? So which is u, the gradient of the displacement, which is essentially what we need to compute in order to compute all the deformation gradients, the various tensors, strain tensors, and so on. You need to compute this quantity, and that is decomposed as an elastic part into an elastic part and a plastic part. Okay, so you can think of this as roughly the displacement gradient, okay, and this as a plastic gradient, plastic displacement gradient. The only problem is that each of these individually cannot be written as the gradient of some function, but the sum of these two quantities can be written as the gradient of some function. Okay, if you were to have an analogy with thermodynamics, so you would write the change in internal energy as the sum of the work done and the heat supplied, but neither of the work done nor the heat supplied can be written as an exact differential, whereas the change in energy is an exact differential. Exactly the same thing, not exactly, so sorry, mathematically they are similar. So a similar kind of situation happens here. Neither beta E nor beta P are gradients of some function. Both of these are second order tensors, but the sum of these two second order tensors is a second order tensor which can be written as the gradient of the displacement field. Okay, and this is the key idea behind the small strain modeling of plasticity, of dislocations in fact. And the rationale behind this is what we saw just now. If you were to model the your body as a crystalline solid, then you see that plastic deformation in fact is the jump of the system from one stable energy well to another stable energy well, and once it jumps, the behavior in the new well is still elastic, but the total strain has to be summed up as the sum of the elastic part and the plastic strain involved in jumping from one well to the other. Okay, good. Once you have this decomposition, what you're left with now is how would you characterize this beta p? Okay, because beta e would come in as the solution of your governing equations, as we will see shortly. Okay, so to compute beta p, remember that this is the total plastic slip, but we know how to model that, and that is exactly what we have idealized as this cut slide paste procedure. So we have modeled this dislocation as follows. You take one part of the crystal, you cut it from the rest of the crystal, you slide it to the right by a definite amount, and then you paste it back. And how much you slide it by? You slide it by exactly one lattice spacing, right? So if you look back at this diagram, so you have actually slid it by one lattice spacing. Okay, you have slid it by one lattice spacing, and the technical term for that is a Burger's vector. Burgers, Burger's vector. Okay, and the standard symbol is small b that you see here. And how would you represent this cut slide paste procedure? So you can represent it as follows. Okay, suppose I have this particular coordinate system where x1 axis is along the slip plane, x2 axis is along the dislocation line, and x3 axis is normal to the slip plane. Okay, now if you notice your plastic slip, there is no plastic slip in this region, there is no plastic slip below, there is only a plastic slip on the top left part, right? In other words, there is only a plastic slip when x1 is negative. So let's introduce a Heaviside step function, and in case you don't remember what the Heaviside step function is, we saw that in the context of statistical mechanics also. It's a function which takes a value 1 if its argument is positive, it takes a value 0 if its argument is negative. Okay, so theta of minus x1 is a quantity which is equal to plus 1 when x1 is negative, and it is 0 when x1 is positive. That's exactly what you want, right? So on the left you want to have a positive displacement, and on the right you want to have 0 displacement. So it's a step function which tells you how exactly you have done the cut paste procedure. This is still the plastic strain, plastic displacement. Okay, and of course you also want to have a theta of x3 here, because you have cut it across the slip plane, so there is no plastic slip below the slip plane. There is only a plastic slip above the slip plane. So the only places where you have a plastic slip are when x3 is positive and x1 is negative, and that is exactly given by the product of these two Heaviside functions. So this quantity theta of minus x1 times theta of x3 is 0 whenever, or rather let me put it differently, it's equal to 1 only when x1 is negative and x3 is positive, and it is 0 every other time. In other words, if you take any point in the shaded region in this cube, then the value of u1p is plus b. In every other part, which is the white region of this particular cube, u1p is 0. And again notice that this is u1. In other words, I'm looking at the slip along this direction, the x1 direction. If I were to look at u2p or u3p, they are all 0 throughout the crystal, because you are not displacing them along the other directions. You are specifically moving the top left block of this particular crystal to the right by a definite amount b, which is the Burger's vector. Okay, so that is the way in which you would do a continuum model of the plastic, the cut slide paste procedure. Once you have this, then the plastic strain beta p can be obtained by simply taking the derivative of this particular term. Okay, for instance, if I look at a beta 1 3 component, then it is considered, computed by taking the derivative of this with respect to 3 direction, or with respect to x3. The only catch here is that u1p is not really your nice smooth function, right? So it's not like a function which is differentiable. So you see that there is a step function. So how do you differentiate such a function? So obviously you will end up with a problem, right? So because if you differentiate this with respect to x1, at this point it's not differentiable, which is why it is not considered as the gradient of a regular function. But if you extend your analysis to include generalized functions, then the derivative of the Heaviside function is precisely the Dirac delta function. Okay, and if you don't understand this, one way to appreciate that is to approximate this particular step function as a sequence of smooth sigmoids. Okay, and then consider the case when the sigmoid gets steeper and steeper, and what would happen then is that each of these derivatives would be a sequence of Gaussians, which are Gaussian like functions which are of increasingly narrow width. In the limit, when the sequence of sigmoids approach the step function, the sequence of Gaussian like functions will approach the Dirac delta function. Okay, that's a very simple way to understand this. So you see now that you have an expression for beta 1p. Okay, in particular you have shown that the 1 3 component of the plastic slip is given by b, which is the Burger's vector, times the Heaviside function, which just tells you where the dislocation is present, times a Dirac delta function, okay, on the x3 direction, which is the top direction. Now the rest of it is very simple. We know that the stress depends only on the elastic part of the strain gradient. Why is that? Again, go back to our example here, and we saw that once the system jumps into the new energy well, okay, so this is the initial energy well. After plastic deformation, it has jumped into a new energy well, and now you see that the total strain is the sum of the elastic strain and plastic strain, but the total stress is only caused by this change. Okay, so if I look at this energy well, that is the ground state, this is the current state. So the stress is going to depend only on the relation between the current state and its parent ground state. So in other words, the stress is going to depend only on the elastic part of the total strain. It is independent of the plastic part. Okay, and that is also what we saw earlier, as the plastic part contributes to zero stress. Good. So if you were to translate that here, then what you would see is that the stress can be written as the uh, elastic strain tensor. Okay, the elastic constants, the tensor of elastic constants. Okay, this is what we would have studied in a course on linear elasticity, and I think I reviewed this briefly in the beginning of this particular course. Sorry, yeah. So the total stress is going to be the product of C and beta E. So notice that C is a fourth order tensor of elastic constants and beta E is a second order tensor. But what is beta E? By our definition, it's the gradient of U minus the plastic strain. But you know now an expression for the plastic strain. Okay, and that is exactly what you computed in this particular case. Okay, so you computed the 1 3 component of the plastic strain in this particular case. You can also compute the other components because you know what the plastic displacement is. Using this, you can compute all the other components of the plastic strain, beta p. So this quantity beta p is completely known. Gradient of u is what you need to compute, okay, because u is your unknown displacement field. So your total stress equals the inner product of the elastic modulus tensor and delta u, the gradient of u minus beta p. So once you have this expression for the stress, and this should be looked at as the three-dimensional generalization of your simple relation that sigma is E times epsilon minus epsilon p. Okay, which is what we saw earlier in the simplified representation that of plastic, how dislocations mediate plastic strain. Once you have this representation of sigma in terms of gradient of u and beta p, then the rest is straightforward. So you just, the equilibrium conditions which we have seen from continuum mechanics is just that the divergence of stress is equal to 0. Because this is a case situation where we are considering a body with a dislocation, but there are no external forces acting on the body. There are no body forces, there are no surface tractions. Therefore, the governing equation is just that the divergence of sigma equals 0. So what happens if we substitute for sigma this expression c times gradient of u minus beta p, then you would have the corresponding expression that the divergence of c times gradient of u is the divergence of, okay, there is a typo here, it should not be beta p, it's a divergence of c times beta p. Okay, now you see that the left hand side of this particular equation is exactly the left hand side that you would have in standard linear elasticity. Okay, so for instance, if you consider an isotropic material, you know how C can be expressed in terms of the Lamé constants. Therefore, you know exactly how the left hand side looks like. Okay, if the material did not have any dislocations, then the plastic strain is 0, and therefore the right hand side is 0, and you recover your standard equations of elasticity. But now, when you have a dislocation present inside the body, the presence of the dislocation manifests itself as an additional body force, even in the absence of any externally applied body forces. Okay, so this particular body force that is present on account of the presence of dislocations. Again, notice that this is del dot c times beta p. There is a c missing here. Please, there is a typo. Please fill in that. So this additional force, body force that you see, which is entirely due to the presence of a dislocation, is an example of what is called as an eigenstress. Okay, and beta p itself is an example of what is called as an eigenstrain. An eigenstrain is a strain without a corresponding stress. Remember that we had epsilon p as a strain present in the material without an accompanying stress. That is an example of an eigenstrain. Now, the corresponding stress which comes in as a body force is an example of an eigenstress. Okay, you will also have a correction term in the boundary conditions when you apply the surface tractions. You will also have an additional c times beta p dot n coming in as a traction force if you work out the details. Okay, but I just want you to look at the larger picture, which is that the presence of a dislocation can be thought of as a homogeneous elastic body subject to a specific kind of a body force. So in other words, I can think of the body with a dislocation as an effective elastic body without any dislocation, but with a body force of this particular form that is shaded here, which is the eigenstress. Okay, and that is the power of an equivalent representation. Once we have this, the solution of this is no different from the solution of regular elastostatics. Right, in standard continuum mechanics, if I were to give you a body in which I give you a particular body force, I tell you that the body is linearly elastic and I want you to compute the elastic fields, you know how to do it. In principle, for instance, you can compute the solutions exactly, or if you cannot, you can compute a numerical approximation using, say, the finite element method. So there are many ways of doing it. So now you essentially have that situation. I have an elastic body subject to a body force. So we can compute the solutions. Okay. Now the solution, it turns out, is a very tedious process. It takes a lot of algebraic details to study this. There is a very nice book called Micromechanics of Dislocations by Toshio Mura. It's an outstanding book that gives you a lot of details about how these calculations are done. Okay, and in principle, what you will do is you would express the displacement field in terms of its Fourier components. It's a basis expansion, and then the Fourier version of this particular equation is going to be much easier to solve, and then you transform it back to the real space coordinates. Okay, and so it's a pretty involved process, but in principle straightforward. And if you do all that and you do all the mathematics and the simplify the algebra, again I refer you to Toshio Mura's book Micromechanics of Dislocations for further details. What you will see is that the stress has this very peculiar behavior. If you choose the origin as the position of the dislocation, okay, which is what we have done so far, then an r denotes the distance from the dislocation, then the stress actually varies as 1 over r. What does this mean? Far away from the dislocation, there is no stress. So if I were to look at this particular body, the dislocation is present here. If I were to look at a point here and find out the stress inside at that point, the stress would be close to 0 because it's very far from the dislocation. But as I get closer and closer to the dislocation, the stress increases, but it increases as 1 over the distance of the point from the dislocation. But what happens to the dislocation itself? The 1 over r function blows up. So in fact, the linear theory of elasticity predicts that the stress is infinite at the presence of a dislocation. Okay, and this is a central result in theory of elasticity. Is it physically correct? No. Okay, in a real material, the stresses can never be infinite. In fact, it is precisely for that reason that you had this behavior, right? So there is an upper cutoff here. Why is there a cutoff? Because the material cannot withstand strength beyond this. And why is that? Remember that these interatomic forces are coming because the atoms interact with each other according to the laws of quantum mechanics. In other words, the electron shells interact with each other, the electrons interact with each other, and that gives you the interatomic potential and so on, right? But there is a definite strength to it. If you supply more energy than that the bond energy present between two atoms, that bond breaks and the system can no longer be cohesive, and that's why you have a finite upper limit. The macroscopic manifestation of that is precisely what you consider as a yield strength. Okay, therefore beyond the yield strength the system cannot withstand any loads, and yet your classical theory of elasticity is now giving you a result that the stress goes to infinity at the position of the dislocation. Okay, now there are two ways of interpreting this. One is of course that this is an idealized theory, and therefore within uh, if the material behavior is completely linearly elastic, then the stresses indeed have to go to infinity at the dislocation core. The other way to look at it is, yeah, sure, it's an idealized theory, but if you look at the region around the dislocation core, which is this region, okay, then it is indeed incorrect to think of the material as linearly elastic. Because if the material were linearly elastic, the stresses go to infinity, but we know that in real materials the stresses don't go to infinity. So this curve has to be corrected close to the position of the dislocation. And the region around the dislocation is a highly non-linear part. You cannot study it with linear elasticity. In fact, going back to our initial uh, diagram here, the photograph here, from the transmission electron microscope, you see that the atoms are all kind of well placed here on the perfect crystal part, but close to the dislocation core they are hazy. And the reason is that they are heavily displaced, and this is a highly non-linear region. So linear elasticity does not work here. It works very well outside, okay, and even at this scale linear elasticity works pretty well, but at the dislocation core it completely breaks down, because if linear elasticity were right, then you would get a an infinite stress. But the very fact that real materials have finite stress means that this theory is no longer valid close to the dislocation core, and you would need to come up with systematic corrections for this particular theory. Okay, good. Now what I have shown here is just a summary of the discussion so far. Okay, that the elastic field of a dislocation is singular at the position of the dislocation according to the linear theory of elasticity. Now this clearly is not a very happy state of affairs, right? So we know that in real materials at the core the stresses cannot go to infinity, so we clearly need to correct this theory. How do we go about correcting this theory? Okay, and that is where a variety of different models have been proposed. For instance, there are what are called as core regularization models, where people remove a region around the dislocation, a region around the dislocation core, okay, and they use linear elasticity everywhere else, and they come up with very interesting mathematical models to remove the singularity in this shaded region, the dislocation core. Okay, so there are non-singular core models due to Weisai, for instance. There are also strain gradient models where, in addition to the stress depending on just the elastic strain, you model it as depending on the elastic strain gradient also. Okay, those models can also help you to remove the singularity at the dislocations. Alternatively, you can come up with an entirely different class of models called the diffuse core models, of which the prominent examples are the Piles-Nabarro model or phase field models, which what they do is they say, okay, fine, the main reason why you see such a singularity is because you model the dislocation as this perfect singularity, right, this sharp line present at the edge of the slipped and unslipped regions. But what if you were to model it as a diffuse slip? So the slip is not happening continuously, I'm sorry, in a sharp manner, but rather it happens in a diffuse manner. It turns out this is also a way in which you can remove the singularity. And the nice thing about this approach, the diffuse score approach, is that it is more realistic. It is in fact closer to how we view slip using transmission electron microscopy images. Okay, and what I want to do in the next lecture is to show in outline how one particular example of this diffuse core model works, and that model is going to be the Piles-Nabarro model. Okay, it's a very nice model which shows you how you can, using linear elasticity and by using some interesting clever models, illustrate the dislocation core structure. Another reason for studying the Piles-Nabarro model is that it is also one of the earliest examples of a multi-scale model, and so I will talk about some aspects of why it is a multi-scale model and how it can provide us, how lower scale simulations can actually provide us information about the dislocation core structure. Okay, those will be the subjects that we will consider in the next lecture. I'll stop this video here.